Good morning, Internet. I am Matt Buyak, and in this video, we'll take a look at the 28th problem from the Project Euler problem archive. So this problem asks a question about the natural numbers arranged in a spiral pattern with 1 in the center and consecutive natural numbers spiraling outward and upward. And in particular, it asks us to find the sum of the numbers along the two diagonals when the grid has dimensions 1001 by 1001. Now, it wouldn't be too difficult to write a program to solve this for us, but I don't think the result would be particularly interesting. And so I'm going to solve this with analysis alone. So let's get into it. As usual, we'll copy our template directory to make our problem directory. And then I'm just going to delete the CPP and the make file because we aren't going to need that. All we need is our analysis file. OK, so going back to their example briefly, I'm going to think of this problem in terms of layers. So a layer is going to be, in this example, the first row, last row, first column, and last column would be the second layer. And then the 7 through 8, 5, 4, 3, and then also 6 and 2 would be the first layer. And so we're going to build up this spiral pattern in layers. 1 is, I guess you would count as the 0th layer, but we're actually just going to handle 1 specially. OK, now the first thing that I'll observe is that in each layer, the largest number is going to be a square. And in particular, a square of an odd number. So you have 1 in the center. 3 is the next odd number, so that's going to be 3 squared. The next odd number is 5, so then 5 squared. And so we can see that the largest number in the third layer would be 49, since that's 7 squared. We can also look at the difference between corner numbers, which is what we're interested in, numbers along the diagonal. And see that in the first layer, the difference is 2. In the second layer, the difference is 4. In the third layer, the difference would be 6, etc. So this makes it pretty easy to determine the value of the corner numbers in each layer. We know that one of them is going to be the square of an odd number, and then the rest are going to be 2 times the layer number less than that square. By that I mean in layer 2, the difference between corners is going to be 4. So we know that we have 25, 25 minus 4, 25 minus 2 times 4, and 25 minus 3 times 4 are the other values. OK, so let me stop blathering and actually write something down here. So we'll say let the current layer be given by L. The largest corner number in a layer will be 2L plus 1 squared. Each of the other corner numbers will be some multiple of 2L less than that. So in particular, the 4 corners will be obviously we have 2L plus 1 squared, as I mentioned. And then we'll have that minus 2L, that minus 4L, and that minus 6L. So the sum of the four corners will be, so that's going to be 4 times 2L plus 1 squared minus, I believe that's, let's see there, we got 12L. Yes. Okay, so we can test this pretty easily. We know that if we look here, let's pull up our calculator. We're going to have 21 plus 25 plus 17 plus 13. So we would expect that the second layer will have a sum of 76. So let's see, 4L equals 2. We have 4 times, it's going to be 5 squared minus 24. And that's going to be equal to 100 minus 24, which is equal to 76. As expected. Okay, so we have this expression for the sum of the four corners in a given layer. Now we need to sum that over all of the layers. So we'll say note a grid with dimensions 1001 by 1001 will have 500 layers. And the way that I got that is just by observing that, if it's 1001, that means that we have the 1 in the very center. And then each layer is going to have both a left-hand side and a right-hand side. And so that's going to be 1001 minus 1 divided by 2 gives us 500 layers. Okay. So the sum for a particular grid, we'll say, let the total number of layers be n. And so we're going to calculate sum, L equals 1 to n of 4 times 2L plus 1 squared minus 12L plus 1. So this is just that 1 in the very center. It's not part of a layer. We're just handling that on its own. Okay, so let's expand this out. So this is going to be 4L squared plus 4L plus 1. And then we're going to multiply this 4 through to give us 16L squared plus 16 plus 4. And then we're going to subtract 12L to give us 4L. And again, we can just double check to make sure we haven't made any mistakes by doing 16 times 4 plus 8 plus 4 gives us 76 as expected for our second layer. And so now I'm going to write this as, I'm going to break this into 3 different sums. And so it's going to be 16 times the sum from L equals 1 to n of L squared plus 4 times the sum from L equals 1 to n of L plus 4 times the sum from L equals 1 to n of 1. Obviously, not actually a function of L, but just to keep this consistent. And then obviously plus 1 at the end. Okay, now fortunately, we have a closed form for each of these sums. The easiest, obviously, is going to be this last one here. Since it doesn't depend on the value of L, this is just going to be 4n plus 1. Now, looking at this second sum here, we know. Let me just say note. The triangle numbers are given by n times n plus 1 over 2, and pyramid numbers are given by, let's see, I believe it's 2n cubed plus 3n squared plus n over 6. And so the triangle numbers are just the sum of the integers, that is this second sum here, and the pyramid numbers are given by the sum of the squares, this first sum here. And I did a previous video on the triangle numbers and the pyramid numbers, and so I'll link to that in the description if you want more details on how we can derive these expressions. But since we've already derived them, it's easy for us to plug those into our expression here. So in particular, the pyramid numbers are going to be 16 times this value. And the triangle numbers are going to be 4 times this value. Okay, so let's see if we can simplify this a little bit. So one thing that I'm going to do is I'm going to so that we can work with integers here. I'm going to this factor of 1/3 in here is kind of obnoxious, and so what I'm going to do is take that out, multiply these other terms by 3, and just add a divided by 3 at the end here. Okay, so this will let us combine like terms, and so we can divide by 2 here and get 8. And we can simplify here, get 6. Okay, and now we can distribute this 8 to get 16 and 24 and 8. And distribute this n to get n squared plus n, and distribute this 6 to get 6n squared plus 6n. Okay. And so now we can combine like terms, as I was saying, to get 16n cubed plus, looks like 30n squared plus 20n plus 3 all over 3. Okay, so we can test this. We'll say note when n is equal to 2, our sum should be, I believe they give, yes, it should be 101. And so we can calculate that as 16 times 8 plus 120. This is going to be 128 plus 40 plus 3 over 3. So 128 plus 120 plus 40 plus 3 divided by 3, 97. We apparently have made some minor mistake. Let me see if I can, we're off by 4. So somewhere we, we've made a mistake. I missed this term here. This should be 26n, and so that's going to give us 52 here. 128 plus 120 plus 52 plus 3 over 3. There we go, 101. Okay, apologies for that minor hiccup. And so that is going to be equal to 101. And so now we can plug in our, 4n equals 500. Sum is equal to so this is going to be 16 times 500 cubed, large number, plus 30 times 500 squared, plus 26 times 500, plus 3 divided by 3. Gives us this monstrosity. And so now we can go back to the archive and confirm, after it finishes loading, that our answer is indeed correct. So that will be it for this problem. In the next video, we'll be moving on to problem number 29.